In control systems, our goal is to manipulate a system's behavior to achieve a desired outcome. Imagine a self-driving car navigating a busy street or a robotic arm assembling components. This is where the Linear Quadratic Regulator or LQR comes in, a technique that designs controllers to drive a system towards a desired state optimally. LQR is particularly well-suited for systems described using linear state space representation, from simple circuits to complex aircraft. As we delve deeper into LQR, we'll uncover the principles and practical details that empower engineers to design robust control systems. Before diving into LQR, let's compare it to pole placement. Both methods aim to stabilize a system and achieve desired performance, but they differ in approach. Pole placement manipulates the closed-loop poles of a system to influence behavior like settling time and damping ratio. LQR, however, considers both the system's states and control inputs in the optimization process. Instead of placing poles, LQR minimizes a cost function that penalizes deviations from the desired state and excessive control effort. While pole placement offers direct control over pole locations, it can be challenging to translate performance specifications into specific placements. LQR provides a systematic way to find the control law that minimizes the defined cost function, often resulting in a more balanced control strategy. However, LQR requires a well-defined cost function and can be computationally demanding. The choice between LQR and pole placement depends on the application, performance criteria, and the engineer's familiarity with each method. At the heart of LQR lies the cost function, a mathematical expression that quantifies the cost of a control strategy. To understand this, consider choosing a transportation method for your daily commute driving, taking the bus, or riding a bicycle. Each option has costs and benefits like fuel expenses, travel time, and flexibility. Similarly, LQR uses a cost function to represent trade-offs in controlling a system. The LQR cost function typically includes state deviations and control effort. State deviations are how far the system's states are from desired values, while control effort reflects the resources required. By assigning weights to these components, we can prioritize aspects of the system's performance. For instance, if minimizing energy consumption is crucial, we might assign a higher weight to control effort. Implementing LQR in MATLAB, a practical guide. Let's delve into LQR's practical implementation using MATLAB. MATLAB simplifies setting up, solving, and analyzing LQR controllers. First, define the system's state space representation, state matrix, input matrix, output matrix, and feed-forward matrix. These matrices describe how the system's states evolve over time in response to inputs. Next, choose the weighting matrices Q and R, which determine the importance of minimizing state deviations and control effort. Q penalizes deviations from the desired state, while R penalizes large control inputs. Use MATLAB's function to compute the optimal state feedback gain matrix K. This gain matrix, when multiplied by the system's state vector, provides the optimal control inputs. For example, define the system matrices A, B, C, and D, and the weighting matrices Q and R. Calculate the optimal gain matrix K using. Once K is calculated, use it to design the closed-loop control system with the control law. This ensures the system's states converge to desired values while minimizing the cost function. MATLAB provides tools for simulating and analyzing the LQR controller's performance. Use functions like, or to observe the system's response to different inputs. Tuning your controller. The impact of Q and R matrices. The choice of Q and R matrices shapes the performance of an LQR controller. These matrices act as tuning knobs, adjusting the importance of minimizing state deviations and control effort. A higher Q value emphasizes minimizing state deviations, leading to a faster response and higher control effort. A higher R value prioritizes minimizing control effort, resulting in a slower response and larger state deviations. Consider a mass spring damper system. A high Q and low R value prioritize minimizing position errors, leading to aggressive control. Conversely, a low Q and high R value result in a slower response with reduced overshoot. The optimal choice of Q and R depends on the application and desired performance. MATLAB simulation tools help visualize the impact of different Q and R values on the system's behavior. Conclusion. Embracing the power of LQR. LQR stands as a cornerstone in optimal control, offering a framework for designing robust controllers. By formulating the control problem as an optimization task, LQR helps find the control strategy that minimizes a defined cost function. Understanding LQR's principles and practical aspects unlocks its potential to address control challenges across various domains. Embrace the power of LQR, experiment with different systems, and gain an intuitive understanding of its capabilities.